For generations, the answer to what is the highest point on Earth has seemed unequivocally clear: Mount Everest. Its iconic silhouette looms large in our collective imagination, a symbol of ultimate natural grandeur and human endurance. But what if that seemingly simple question holds a more complex, multi-layered truth? What if highest isn't a singular, universally agreed upon metric? Our investigation begins by challenging this foundational assumption, probing how different scientific approaches lead to vastly different, yet equally valid, claimants to the title of the world's highest point. When most people speak of the highest point, they refer to elevation above sea level. By this widely accepted convention, Mount Everest reigns supreme. Located in the Mahalanga Himal subrange of the Himalayas, straddling the border between Nepal and China, its formidable presence is undeniable. This metric, while intuitive, is a product of early cartography and naval navigation, where sea level provided a convenient and relatively consistent baseline. It has shaped centuries of exploration and mountaineering, establishing Everest's legendary status as the roof of the world. The precise measurement of Everest's elevation has been a subject of rigorous scientific debate for decades. After extensive surveys, including GPS technology and ground-penetrating radar, the official height was jointly declared by Nepal and China in December 2020. This consensus figure solidified Mount Everest's position within the sea level standard. Understanding this precise measurement is crucial for appreciating the scale of human endeavor in surveying these extreme environments and for providing a definitive benchmark for this particular definition of highest. However, the very notion of sea level as a consistent baseline introduces a critical nuance often overlooked. Earth is not a perfect sphere, it's an oblate spheroid, meaning it bulges at the equator and is flattened at the poles due to its rotation. This subtle, yet significant, geological reality means that points at the equator are inherently further from the Earth's geocenter than points at higher latitudes, even at the same elevation above sea level. This fact fundamentally reconfigures our understanding of highest, prompting a re-evaluation of Mount Everest's undisputed claim. The difference created by Earth's equatorial bulge is not negligible. The equatorial diameter is approximately 43 kilometers, or 27 miles, greater than the polar diameter. This means that a point on the equator is inherently thousands of meters further from the Earth center than a point at a pole, even if both were at sea level. This substantial difference forms the basis for an alternative definition of highest point, one that challenges the sea level paradigm and highlights the complexities of planetary geodesy. It's a scientific reality that reshapes our perception of geographical extremes. Enter Chimborazo, an inactive stratovolcano in the Andes Mountains of Ecuador. While its peak rises a respectable 6,268 meters above sea level, placing it well below Everest by conventional measures, its proximity to the equator grants it a unique advantage. Due to the Earth's equatorial bulge, Chimborazo's summit is, in fact, the furthest point from the Earth's geocenter. This geological quirk makes it the highest in a strictly geocentric sense, a distinction recognized by a subset of geographers and astronomers, redefining what it truly means to be at the apex of our planet. Measurements taken via GPS and other advanced geodetic techniques confirm Chimborazo's unique claim. Its summit is approximately 6,384.4 kilometers from the center of the Earth. To put this into perspective, despite being significantly lower in terms of elevation above sea level, Chimborazo literally pushes the boundaries of our planet's physical form further into space. This data underscores how the choice of a reference point drastically alters our perception of highest, highlighting the scientific precision required to make such definitive statements about planetary features. Let's compare these two titans directly under the lens of distance from Earth's geocenter. Mount Everest, despite its commanding sea level height, is located at a higher latitude, where the Earth's curvature pulls points closer to the center. Chimborazo, positioned near the equator, benefits from the planet's substantial bulge. This comparison clearly illustrates the profound impact of Earth's oblate spheroid shape on geographical measurements, revealing that the highest point is not merely a question of how far it reaches into the sky, but also from what baseline you begin measuring, and how the planet itself is shaped. Our quest for the highest point takes another turn with a third, equally compelling definition: total height from base to summit. If we consider the entirety of a mountain, including its submerged portions, the Hawaiian island volcano of Mauna emerges as an astonishing contender. The vast majority of this colossal mountain lies beneath the Pacific Ocean, its true scale hidden from casual observation. This perspective shifts the debate from elevation above a sea level datum to the sheer geological mass and vertical extent of a single structure, offering a radically different view. From its base on the ocean floor to its summit, Mauna Kea stands at an astounding 10,210 meters, or 33,500 feet. For context, while its visible portion above sea level is only 4,207.3 meters, its true geological footprint extends dramatically deeper than any other mountain on Earth. This measurement fundamentally redefines our perception of mountain height, challenging the traditional focus solely on what is exposed to the atmosphere. It compels us to consider the full vertical extent of a geological feature, not just its visible tip, revealing a submerged world of monumental scale. Comparing Mount Everest to Mauna Kea based on total height from base reveals a stark difference. Everest, while impressively high above sea level, rises from the Tibetan Plateau, an already elevated landmass. Mauna Kea, in contrast, originates from the vast depths of the Pacific Ocean floor. This comparison underscores how our understanding of highest is inherently tied to the chosen starting point. Is it the height relative to a dynamic global sea level, or the total structural elevation from a geological foundation? This question has profound implications for how we classify and appreciate Earth's grandest features. The case of Mauna Kea highlights the often overlooked role of the ocean in shaping our planet's topography. Over 70% of Earth's surface is covered by water, concealing an entire world of mountains, valleys, and abyssal plains. Many of the planet's truly colossal geological structures are therefore hidden from plain sight, only revealed through advanced bathymetric mapping and deep-sea exploration. This raises a fundamental question. Should our definition of highest be limited by the arbitrary boundary of the air-sea interface, or should it encompass the full majesty of Earth's geosphere? The debate over the highest point is more than a trivial academic exercise. It reflects profound differences in how we define and measure our world. Is it the point that offers the most challenging ascent for climbers, pushing them furthest into the thin atmosphere? Or is it the geological behemoth, whose sheer volume and vertical extent dominate the planet's crust? Perhaps it's the point that protrudes furthest into space, a testament to Earth's dynamic, rotating form. Each definition holds validity, dependent on the context and the specific scientific inquiry being pursued. For mountaineers and adventurers, the highest point unequivocally remains Mount Everest. Its immense altitude above sea level dictates the extreme physiological challenges of climbing, demanding specialized equipment, months of preparation, and often, risking life itself. The oxygen deprivation, brutal winds, and freezing temperatures are directly tied to its vertical reach into the stratosphere, making it the ultimate test of human endurance. From this human-centric, experimental perspective, Everest's reign as the highest remains undisputed and profoundly impactful. The human endeavor associated with Everest is staggering. Since the first confirmed summit by Tenzing Norgay and Edmund Hillary in 1953, thousands have attempted the ascent. As of recent data, the total number of individual summits exceeds 11,000, yet the mountain has claimed over 300 lives. These statistics underscore the unique dangers posed by its extreme elevation, reinforcing its status as the pinnacle of mountaineering achievement. It is a stark reminder that while other mountains may be higher by different metrics, Everest remains the undisputed king of atmospheric challenge. The disparity between public perception and nuanced scientific understanding is evident in this discussion. While Everest is the highest is ingrained in popular culture, geological and geodetic sciences offer alternative perspectives based on different, equally valid, measurement parameters. This isn't about discrediting Everest's grandeur, but rather enriching our understanding of planetary topography. It highlights that scientific inquiry often leads to more complex answers than initially perceived, encouraging us to look beyond simplistic labels and appreciate the multifaceted nature of Earth's extreme points. To further illustrate the spectrum of Earth's extremes, it's worth briefly considering its deepest point. The Mariana Trench, located in the western Pacific Ocean, is a crescent-shaped oceanic trench that defines the deepest natural point known on the surface of Earth. Its sheer depth, similar to Mauna Kea's submerged height, forces us to confront the vast, hidden dimensions of our planet. This symmetrical extreme reinforces the idea that true geological scale often extends far beyond our immediate atmospheric or terrestrial experience, pushing the boundaries of human exploration and understanding. The Challenger Deep, the deepest known point within the Mariana Trench, plunges to an astonishing 10,984 meters, or 36,037 feet, below sea level. This makes it significantly deeper than Everest is high above sea level. This profound depth is a testament to the immense pressures and geological forces at play in our planet's crust. Comparing this figure to the heights of Everest, Chimborazo, and Mauna completes our picture of Earth's vertical scale, reminding us that for every peak, there is an equally impressive, often more vast, abyss. Our investigation reveals that the highest point on Earth is not a singular, simple answer, but rather a multifaceted concept defined by the parameters of our inquiry. Mount Everest holds its title for elevation above sea level, a monumental feat for human endeavor. Chimborazo claims the prize for being furthest from Earth's geocenter, a direct consequence of our planet's rotation. And Mauna stands as the tallest mountain from its true base, a submerged giant revealing the hidden scale of our world. Each perspective offers a valid, yet distinct, truth. This complexity isn't a weakness. It's a testament to the Earth's dynamic geology and the continuous evolution of scientific understanding.